Greetings. So, today we will discuss the proof for the Stokes theorem. We have already defined the curl of a vector, and we will find that it has got fascinating applications in fluid mechanics, electrodynamics and so on. So, this is how we defined the curl of a vector. We defined it in terms of its components along a unit vector, and when you consider three such unit vectors which form an orthonormal basis, then this gives you a complete definition for the curl of a vector, and it is defined as the limiting value of the circulation per unit area. And we have already discussed how the direction of the unit vector is related to the area that we are talking about, because an infinitesimal area is treated as a vector having a given direction, and the direction is connected to this vector of the unit vector through the right hand screw rule, so which we discussed in our previous class. And with this giving us a complete set of orthonormal base vectors, these components give us the complete definition of the curl of a vector. Now, what we do here is we multiply both sides by the magnitude of this area, delta S. So, on one side you get this circulation which is here, and on the other side this curl A dot n is multiplied by the magnitude of the surface element, and this magnitude of the surface element together with the direction surface of that surface element give you the vectorial surface element delta S. So, you get the dot product of the curl of the vector with the vectorial elemental area. So, this is a very straightforward relationship, and what we can do is apply this definition to small segments as well as large segments, and this is an extremely fascinating application. It is a very simple one, but what it does is it allows us to prove the Stokes theorem in an extremely simple manner. We do not have to do any complicated analysis. It comes straight out of the definition of the curl of the vector, which is in this relationship at the top. So, this is defined in terms of the components of the components of the curl of the vector are defined as the circulation per unit area in the limit the magnitude of this area tends to 0. And if you have got a piece of area like this, you can just draw a segment in between and then divide this into two pieces. Moreover, you can divide each of these pieces, each of these two pieces into a number of tiny tits and bits of elemental areas. They do not have to be of any regular shape, they can be quite crooked, which is convenient for an artist like me, because you do not have to worry about the geometry and the shape of the elemental areas, etc. So, one could have 4 sides, another piece could have 5 sides, or it does not matter. So, as long as you make tiny tidbits of elemental areas, and then what you will have is, if you take any of these small pieces of areas, so if you have a piece of cloth or any handkerchief or anything that you stretch it out and then you divide it into these small segments, you take a tiny piece of that, and to this tiny piece, and in this picture this tiny piece is shown over here, which as you can see does not have any regular shape or anything of this kind. It is not even flat, because the surface could have been pinched and it has some wiggles ups and downs, it does not matter. And this elemental area will have a certain direction corresponding to the right hand screw rule. So, if you traverse the boundary of this area along this, a right hand screw would propagate upward in this figure, which will be the direction of that elemental surface area according to the right hand screw rule. and you can apply this definition of the curl of the vector to this tiny piece of area. But then you could also apply it to any neighboring element like this one, or the one on this side, or the one on the other side, or the one on this side, and you will find that each neighboring pieces will have this path integral, the circulation traversed in opposite directions, like you see in this figure over here. The piece on the right side is traversed from top to the bottom, as you see in this figure, and the piece on the left side is traversed from bottom to the top in this figure. So the contribution to the circulation by these two pieces will cancel, because dl is a vector elemental displacement along that path, and this obviously has opposite directions when you traverse it on the left side or on the right side. So all of these inner paths will, the contribution to the circulation to these inner paths will cancel, and you will be left only with the net circulation determined along the edge, along the outer perimeter of this surface element. So what we have done is broken these pieces into these tiny bits, and given the fact that all of these inner contributions cancel each other, then the net circulation A dot dl over the closed path C, which is this outer path, okay, this is the path C. Notice that this letter C is written over here. This is the outer path which goes along the perimeter of the net area, along the outer boundary, and this is written as a sum of these circulations over all of these inner boundaries of these small tidbits of elemental areas. So you sum over I going from 1 through n can be as large as you want, and all of these inner circulations are over these inner boundaries, with the difference that when you carry out this sum from I going from 1 through n, all the contributions of the inner boundaries will cancel each other, and then they will add up to a net result which will be given by the circulation of this vector over the outer boundary. And by this definition, this will give you the component of the surface integral of the curl of the vector along ds. Okay. So it is a very simple proof, and essentially you have this net result now, that if you take the dot product of curl of a vector along this surface element and integrate, because when you carry out these summations from I going from 1 through n of all these small elements and let n tend to infinity, then in the limit this sum will generate the corresponding integral. Okay, it will generate the corresponding surface integral. So you have the net result that the circulation over this closed path, which is the outer edge, is given by the surface integral of curl of A dotted with the elemental surface area over these tiny tidbits, but then you integrate over the entire surface. Okay, this integration of the entire surface is what is implied in this summation I going from 1 through n. Okay. So this result is known as the Stokes theorem. So we have a complete proof for this, and this proof has popped straight out of the very definition of the curl of the vector. We did not have to add anything further to it, and this is an extremely important theorem in vector calculus, which connects the surface integral to a circulation over a closed path. It will remind you, for those of you who have studied complex analysis, it will remind you of the Cauchy's theorem, and what it does is it connects the properties along the boundary of a region with what is inside it. So that is a connection, and it is very rigorously quantitatively established in terms of the Stokes theorem. So this is our net result. What is amazing is that it can be applied to any shape of the surface element. So, this surface is a butterfly net, it is obviously not a flat surface, but it is a surface nevertheless. It could be flat, you could pinch it, pull it up or down, or you can pinch a part of it and pull it down, pinch the other part and pull it up. It does not matter what happens to the surface element, because the rim of this, the perimeter, the outer edge is the same, and no matter what shape the surface elements take, these individual tiny surface elements on the net take, the outer perimeter is the same. So, no matter how this shape is distorted, the left hand side is equal to the same. So, each right hand side will also be the same no matter how you flex that particular surface. So, this will remind you of this butterfly net, which you can distort into various shapes. The only thing to be remembered is the right hand screw convention, because so far as the circulation is concerned, it is along a path which can go either one way as shown in this, or in this other figure it is shown in the opposite direction, and depending on whether you take the upper path or the lower path, no matter how this shape is distorted in between, it may have some wiggles, but the edge of the surface is essentially the same, and you must follow the right hand screw convention to link this direction of the surface element, and that is given by this arrow, because the right hand screw would move forward in this direction by this blue arrow if this path is traversed along this, and if this path is traversed in the opposite direction, then the right hand screw would come in the opposite direction. So, these are the only two things that you have to remember. So, the direction of the path integral is connected to the direction in which this surface is associated, because it is a vector surface element and it has got a direction, and it could be either upward or downward. It is normal to the surface, that so far so good, but there are two normals at any point to a surface. It could be pointing one way or the other way, and there is no ambiguity about it, because that is pinned down by the direction in which this circulation path is chosen, and then following the right hand screw convention as we have defined. The only thing is that the surface must be an orientable surface. So, there are non-orientable surfaces. We discussed some of this when we did unit 8, but I would like to remind you that surfaces which are orientable can be considered. There are certain non-orientable surfaces which we say are not well behaved, and those surfaces have to be eliminated from this consideration. So, the example for this is a cylinder which is open at both ends. This is not a well behaved surface, because you cannot pin down a unique direction to an elemental surface on this on the wall of the cylinder if it is bounded by two edges, because you can take the paths along these two edges so that they will generate a conflict so far as the direction of the surface element is concerned. So, this is not a well behaved surface, but if it is a surface which is open only at one end, so the bottom edge is now closed and you have a top edge, and there is no ambiguity with this. So, this is a cylinder which is open only at one end, and no big deal about it, because this is anyway just like the butterfly net already. So, it is the same example that we consider. So, there is no difficulty with a cylinder which is open at one end, but for a cylinder open at which is open at the top face and the bottom face, then that surface has to be eliminated. Also, there may be a strip which I showed when we discussed unit 8. There may be a strip, we discussed the construction of this may be a strip. All you do is to take a strip of paper, stretch it out, twist it, and then join the two edges, and what happens is that you have this top edge, which if you run your finger at the top edge beginning over here, then follow the path, and then without lifting your finger you find that you end up arriving at the bottom edge, and then you cross it over here, and again without lifting your finger you find that you go over to the top edge. So, there really are not two edges, there is a single edge. Likewise, if you put your finger on what looks like an inner surface over here just underneath this arrow and run this finger as I am showing by this pointer inside the Möbius strip, but then over here you keep going on that, and you find by the time you come over here you find yourself going to what you would otherwise call as the other side, but since you have not lifted your finger you are going to have to admit that it is really the same side. So, this does not have really two sides. So, this is not a well behaved surface, and you cannot apply the Stokes theorem to such geometries. Now, we already got the expression for the curl in the cylindrical polar coordinate system, we got it for the Cartesian coordinate system. Let us get it in some of the other coordinate systems, it is not at all difficult. So, let us do it for the cylindrical polar coordinate system, and I will not spend too much time doing this. I will show the result to you in a hurry, because what all you do is write the expression for the gradient in the cylindrical polar coordinates, and this we have done in great details. We found how to get this expression. You do not have to by heart this expression. All you have to do is to use the idea of a directional derivative, connect it to the idea of a gradient, and from this connection you can easily get the expression for the gradient in any coordinate system. So, you do not have to by heart these formulae, please do not do it, try to get it from first principles by using this idea of a directional derivative and how it connects to a gradient. So, this gradient operator in the cylindrical polar coordinate system is given by E rho del by del rho plus E phi 1 over rho del by del phi, and then you must add the E z del over del z, and then take the cross product of this vector now represented in the polar coordinates. So, you have got E rho a rho plus E phi a phi plus E z a z, but then the vector a is a point function. So, each component could be a function of the particular point represented by 3 degrees of freedom in cylindrical polar coordinates. These are the rho, phi and z coordinates. So, this is the quantity you now have to determine. All I have done is to separate out these 3 terms. So, you have got E rho del by del rho cross this whole vector, then you have got the second term, and then you have got the last term. So, we will carry this to the top of this slide, and now these 3 terms again we separate out one by one. Okay. So, we write it explicitly for E rho del by del rho and construct this cross product with these 3 components. Likewise, take the middle term over here and construct the superposition of these 3 components, and then you take the last term over here and again take the cross product with these 3 terms. Now, this is not an ordinary cross product of 2 vectors, because this side what is in this rectangular bracket is of course a vector, but over here is not a vector, this is a vector operator. So, it must satisfy the vector algebra as well as operator algebra. The operator under consideration is a differential operator. You take the derivative with respect to rho in the first term, you take the derivative with respect to phi in the second term, and you take the derivative with respect to z in the third term. So, these are differential operators, and what you must therefore do is, before you construct the cross product, take the derivatives, do the calculus first and then the vector algebra next. Okay. So, find out the derivatives on this side. The reason you have to do it is because, unlike the Cartesian unit vectors which are constants, the cylindrical polar unit vectors E rho and E phi, they are not constants, they do change from point to point. So, they do not in fact change with respect to rho, but they do change with respect to phi. So, they do change from point to point with respect to the azimuthal angle, and this we have done in considerable detail when we did unit 3. So, you already know how to do this very elementary derivative operation. So, you can take the derivative with respect to rho of E rho A rho plus E phi A phi plus E z A z, and then plug in the results. So, this is the differential operator that you must operate first, and you carry out these differential operators, and then once you have the results, collect all the terms in E rho, collect all the terms in E phi, and collect all the terms in E z. So, some of the intermediate steps I will skip, you can easily work them out in your notebooks, or if you are cleverer than that, please do it in your mind, but you will have the same result quickly enough. So, this is your end result, and we now have the complete expression for the curl of a vector in the cylindrical polar coordinates. Every parameter on the right hand side over here is in terms of the polar coordinates. They involve the polar coordinates of the vector A and the derivatives with respect to the polar coordinates rho phi and z, and the directions are also given in terms of the unit vectors of the cylindrical polar coordinate system. Now that you know the technique of how to get the expression for the curl in any polar coordinate system, you can also get this in spherical polar coordinate system. So, that will be our next task. So, again we have written the expression for the gradient operator in the spherical polar coordinate system. We have done this in detail in unit 3 again, and you follow exactly the same procedure as we did for the cylindrical polar coordinates. Get the differential operators to operate first, and finally do the cross product at the end, and if you just follow that procedure step by step, you will get the net result. Do not forget the scaling factors in the denominator, and once you do that, you will get the end result, which I will let you work out for yourself. So, this is the expression for the curl of the vector in the spherical polar coordinate system. Now, let me suggest to you that there is an important identity which is very often used in vector calculus, that if you have the curl of a vector and you subsequently take its divergence, because you can always take the divergence of a vector. So, if you take the divergence of curl of any vector, then the result is always 0 no matter what this curl is of, okay. No matter which vector this curl is of, the divergence of that curl is always 0, and you can see this result very easily. We will prove it using Gauss's divergence theorem, which connects the volume integral of divergence of a vector with the surface integral of that vector, with the difference that the vector under consideration is the curl of a vector, but it is a vector nevertheless. The curl of a vector defines a vector point function, and you can apply the Gauss's divergence theorem for this curl of the vector, which is exactly what is done in this equation in front of you, and this volume integral is then equal to the surface integral over the surface which encloses the corresponding volume of the dot product of that vector with a surface element, and for a closed surface there is no ambiguity defining the direction of the surface element, it is always the outward normal. So, there is no ambiguity here. So, this is the divergence theorem, and if we apply it to any region of space, no matter what the shape of this region is, it really does not matter, it does not have to be any regular shape, and the proof for this particular identity comes in a very simple manner. If you just construct some path about this volume region, on this volume it does not have to be a regular path which looks like an ellipse in this figure, it could be any crooked path, it does have to be a closed path, okay. So, you take some closed path, it does not have to be in between, it can be anywhere, because for an irregular shaped body there is nothing that you can define as in between, because there is no center of symmetry of any kind, there is no reflection symmetry, okay. So, there is no real symmetry of any kind. So, it does not matter where you take it, all you do is to just construct one closed path somewhere along the surface. So, if it is this bottle, you which is a closed thing, you can take a thread and run it along like this, then run it down over here, then run it over here, then run it over here, and then bring it back over here, and you have got a closed path. So there is nothing regular about the path that we are talking about. Okay, all you do is you divide this closed surface into two pieces, one which is on one side of this path and the other which is on the other side of the path, and these are not two equal regions, they are not equal in any sense, they are not symmetrical in any sense, but they are two. What they do share is a common boundary, which is this. And what you can do is, if you think of a path which is going along the direction shown here. So on this leg it is going from the bottom to the top on this leg, but you can also construct another path which is going from the bottom to the top from the other side. So it will end up, when you take this path over the closed loop, these two paths are in opposite directions. Okay? So these two paths are in opposite direction, and with reference to these two paths you can now define the direction of the surface element. So this surface element with reference to this blue arrow is an arrow pointing to the left, and with reference to this red arrow it is an arrow pointing in this direction, right. That will be the direction suggested by the right hand screw rule. The shape of the surface, mind you, it is like a butterfly net, you can pinch it upward and downward, so no big deal about it. So it could be any irregular shape. Now if you apply the Stokes theorem to these two surfaces, S1 and S2, S1 is this surface which is on one side of this path, S2 on the other side, then the net surface integral over this closed path is equal to the sum of the surface integrals over the surface S1 and S2, because the surfaces S1 and S2 is precisely what together generate the closed surface. Okay. So the closed surface is made up of two pieces, one is the piece S1, the other is the piece S2. So this is a complete identity, and now these surface integrals over S1 and S2 you can define in terms of the circulations using the Stokes theorem. So here is the result. So the surface integral over S1 is the circulation A dot dl over the path C1, and this surface integral over the surface S2 is the circulation of A dot dl over the path C2, with the difference that C1 and C2 are opposite paths, and they being opposite paths, the direction of this elemental increment dl on that path, this one and this one will always be opposite to each other, and the corresponding pieces in the two integrals will cancel each other, the net result will be 0. So what does it tell us? That this surface integral vanishes, this is coming over here, okay, on this right hand side. Now if you go back and look at this equation, you have a right hand side which is identically 0 no matter which volume integral you are looking at. So the corresponding integrand must be identically 0. Okay. This particular identity is going to hold good no matter what shape you have in mind, no matter what volume you have considered, and if it is as general as that, then it guarantees that the integrand itself must be 0, which is the identity that the divergence of the curl of a vector, this is the divergence of the curl of the vector, it must be identically 0. So this is a very useful identity which one employs quite a lot in vector calculus and in electrodynamics and many other applications. So this is your result, that the divergence of a curl of a vector is always 0. We also considered some of these definitions earlier in unit 8, but I will quickly remind you these definitions, because we will be dealing with ideal fluids when we get to the discussion on the Bernoulli's principle. And to define the ideal fluid, we need to have these three definitions: what is tension, what is compression, and what is shear. So, if you consider the force on any tiny elemental area delta A, and you can orient this strip any which way, it could be like this strip or it could be this tilted strip, and accordingly it would have a direction which is normal to that particular surface element. And the definitions are provided over here, that if you consider the stress at any point P, and if you consider the component of the stress in the direction of the unit vector which is in the direction of an elemental area, of a surface elemental area, then if it is equal to the magnitude of the surface, if it is equal to the magnitude of the stress, then you say that the stress is tension. If it is orthogonal to it, if it is 0, then we say it is shear, and if it is equal to the negative of the magnitude, then you say that the stress is one of compression. And an ideal fluid is one, this is the definition of an ideal fluid, that it is one in which the stress at any point is essentially one of compression. So, this definition we had used in unit 8, and we need it one more time, and hence the quick recapitulation over here. So, we will be using the curl of the vector. We have already stated that it is an extremely important quantity, and in fact there is a very important theorem in vector calculus which is known as the Helmholtz theorem. What it tells us, that to define a vector field you need both the divergence of that vector as well as the curl of the vector. Knowing only one or the other is not enough, you need both of them, and furthermore you also need some boundary conditions, but that is a matter of detail. Okay. So, these boundary conditions are also required, but most certainly you do need the divergence of the vector, you also need the curl of the vector, and both together will define what a vector field is, which is why when you want to ask yourself what is an electromagnetic field in a certain region of space, then it is given in terms of the divergence of the vector as well as the curl of the vector, and these are provided by Maxwell's equations. So, we are preparing the background to introduce the Maxwell's equations in the next unit. Okay. So, right now we will first consider an application of the curl in the Bernoulli's, in the derivation of the Bernoulli's principle, and that is what we will discuss here. And I would like to share this with you because there are several Bernoullis who were brilliant mathematicians and brilliant physicists, so many of them, and they were all related to each other, they all came from the same family. What a distinguished family this must have been. So, there were these two brothers, Jacob I Bernoulli and Johann I, and then Johann had children, these three, Nicholas, Daniel and Johann II. This is Johann I, this is Johann II, and the children of Johann II were Johann III and Jacob II. So, they use the same name, so you have to be very careful about not only which Bernoulli, but you also have to keep track of which Johann and which Jacob. So, there are several Bernoullis, a few Jacobs and a few Johanns, and the Johann I is the one, this is the Bernoulli, he posed the famous Brachistochrone problem to Isaac Newton, and Newton was of course able to solve it. So, he was brilliant enough to be able to challenge Newton with a problem, but the Bernoulli's principle that we are talking about is after Daniel Bernoulli, who was the son of Johann I. Now, Johann I was brilliant not only because he posed the Brachistochrone problem, but he also came up with this rule which we recognize as the L'Hospital's rule. I do not know how this is read. Marquis the L'Hospital's rule. This is a very famous theorem in differential algebra. When you take the derivatives, if you have an indeterminate quantity, you can take the derivative of the numerator and divide it by the derivative of the denominator, and then from that ratio you can get the indeterminate quantity which originally you believed was indeterminate. So, this is known as the L'Hospital's rule, but this rule was in fact invented by Johann I, and he entered some sort of a financial arrangement with L'Hospital, entered a financial arrangement with Johann Bernoulli, and the result is that although it was formulated by Johann Bernoulli, it got to be described as L'Hospital's rule. So, you could buy theorems in those days and sell them under your own name. So, it was a different business strategy altogether. So, the Bernoulli we are talking about is Daniel Bernoulli, who is known to have stated that it would be much better for true physics, no, not much better, he just said it was better. It would be better for true physics if there were no mathematicians on earth. So, I quote this with due apologies to mathematicians amongst you. I have nothing against mathematics, I love mathematics and I think it is an integral part. I do not like to distinguish it from physics. Galileo told us that it is the language of physics and you would not really separate one from the other, but Daniel Bernoulli had his own ideas about mathematicians and he did not want them for true physics. So, anyhow, so let me use another little piece of differential calculus over here, and here I consider the time derivative of the velocity. This of course is the acceleration. Okay? This is the acceleration which goes into the cause effect relationship of Newtonian dynamics. This is the acceleration which goes into the linear response formalism of Newtonian dynamics. Now, if this velocity of a liquid is a function of time, it could be a function of time on two counts. One is because it would be a function of the position of a drop of that liquid which is in motion, and therefore its position is a function of time. This is what makes the velocity an implicit function of time, but it can also be an explicit function of time because this velocity could also change not only with the drop of the liquid which is in motion, but also from time to time. It could change from season to season. For example, in the river in the monsoon season here in India, this water speeds would be quite high when the waters are flooded, whereas in summer it could be low. In fact, there could be no water at all if it is a bad summer, right. So, there would be no velocity to talk about. So, obviously, it is a function of time, it would be an explicit function of time. So, here you are talking about a quantity which has got both an explicit dependence on time from this parameter and an implicit dependence on time from here, and this position vector can be written as a function of 3 degrees of freedom, which in Cartesian geometry would be x, y and z. And now if you take its time derivative, then you have to take it term by term, use the chain rule. You first take the partial derivative of velocity with respect to x and then the derivative of x with respect to time. Likewise, you take the partial derivative of this velocity with respect to y, del v by del y, and then the derivative of y with respect to t, because the drop of water itself could be in motion, and then you have got the third term coming from del v by del z and then dz by dt, and the last term is coming from the explicit dependence of the velocity on time. So, here you have these 1, 2, 3 and 4 terms which give you the acceleration of the liquid. And if you look at what is inside this loop here, if you just look at these 3 terms, then you can write this in a rather simple form, which is v dot del operating on the velocity, and the fourth term is the partial derivative operator del by del t, which is here operating on the velocity. In other words, the differential operator d by dt is completely equivalent to the operator which is inside this rectangular box, which is v dot del plus del by del t. So, this is known as the convective derivative. The reason it is called as convective derivative, the term convection will remind us that there is a certain flow which is involved. In convection currents, heat is conveyed, okay, it is conveyed physically by the transport of the gas molecules or the liquid molecules. So, that is how the convection currents are set up, and because it is that kind of motion which is coming into the picture, it is coming from this dx by dt, dy by dt, dz by dt, and it is because of this that this is known as the convective derivative. So, d by dt, this differential operator, is completely equivalent to this v dot del by del t. And now we have got all the tools with us, all the algebra, all the differential calculus with us, all the vector calculus with us, and all we need to do is to do a little bit of very simple manipulation of these terms, and what will come out of it is the Daniel-Bernoulli's theorem. So, we will use the result which we derived in unit 8, that the convective derivative was given by the ratio of this gradient of the pressure divided by density with a minus sign, and the gradient of some external potential, which in our case was the gravity. Okay. So, this result we have derived explicitly in unit 8, and I will just remind you of that result and use it along with another vector identity which I will not prove. But if you determine this quantity in any coordinate system, you will find that the result follows, and you already know how to take the gradient in Cartesian coordinate system, you can do it in spherical polar coordinate system, you can do it in cylindrical polar coordinate system, it does not matter. The result is completely independent of the coordinate system, and the result I want to use is this identity, that if you take the gradient of a scalar function which is expressible as a scalar product of two vector functions. So, A is a vector function, B is another vector function, and you take their inner product or the scalar product or the dot product, these are all equivalent terms, they are all synonymous in our context. Then it is given by this identity, you can write it as a sum of 4 terms, A dot del operating on B, B dot del operating on A dot curl of B, and B cross curl of A. This is A cross curl of B and B cross curl of A. Okay. So, these are the 4 terms that come out of this identity, and we will use this identity to the special case when both A and B are the same vectors, namely the velocity. So, this is quite general, no matter what A function is and what the B function is. So, we might as well apply it to the special case when both A and B are the same, not only they are the same, but they represent the velocity of the fluid, because that is the quantity we are interested in. So, the left hand side of this identity will be the gradient of V dot V, and this is equal to, just I replace A by V. So, V dot del, and this B is also replaced by V. Likewise, I replaced every A and B over here by V, and now I have these 2 terms to be the same because both are V dot del operating on V, and here these 2 terms are also the same. So, if I divide both sides by half, I get half of the gradient V dot V, which is equal to V dot del operating on V plus V cross curl of V. So, this is an identity that I will make use of. And where do we want to use it? We will replace this operator V dot del over here. Okay. So, V dot del operating on V is given by this term, which will be half of this minus V cross curl of V, So, that is what I have got over here. This is half of the gradient of V dot V minus V cross curl of V plus del V by del T, which is this term, and the right hand side is given by this ratio, negative gradient of the pressure divided by the density minus the gradient of an external potential, which we have chosen to be gravity. So, this result is easily derivable, and we are getting closer to the Bernoulli's principle, in which I have used this identity and I have used the convective derivative, and the right hand side comes from the equation of motion for the fluid, which we had established in the previous unit. So, it is the same relation which I have brought to the top of this slide, so that we do not lose any term in our analysis. Now, as would be obvious to you, if the density of the fluid is not changing very much from point to point, then this ratio of the gradient of the pressure to the density can also be written as a gradient of the pressure divided by the density, because if the density is not changing from point to point, it is like a constant, right. So, that makes it easy to write this term, that this half gradient of V dot V is here minus V cross curl of V is here, the del V by del T is here, and this term del P over rho is written as gradient of P over rho with this minus sign, which is brought forward from here, and the last term is minus del phi, which of course survives. Okay, we better carry it forward. And these two terms on the right hand side, both are gradients of appropriate scalar functions. So, we can combine these two terms and write this collectively as the negative gradient of this term plus the scalar function phi, which is the external field, which is the gravitational potential in our case. So, all I have done is to combine these two terms. Now, let us again carry this result to the top of the next slide, so that we do not lose any term, which is all which has been done on this slide. Let me quickly remind you that in the rotating frame of reference, the time derivative operator, when it operates on a position vector, gives you the velocity in a rotating frame of reference, and to this, if you add the cross product of the angular velocity of the rotating frame with the position vector, you get the corresponding velocity in the inertial frame of reference. This is a result which we discussed in our previous class as well. We derived it at great length in unit 5, and this is a quick reminder of the fact that when you do this, you got the velocity in the inertial frame of reference to be given by the velocity in the rotating frame of reference plus this omega cross r term. And now we will take the special case in which this velocity in the rotating frame of reference disappears, but before we do that, let us take the curl of this vector. You have got an identity over here, okay, in which you need the curl of a vector which itself is described as a cross product of two vectors. So, we should know how to take the cross product of two vectors. Now, how do we do that? We make use of an identity, which again I will not prove, but I have already discussed how to get the curl of a vector in any coordinate system. So, you can define the cross product of these two vectors in any coordinate system and take its curl in the corresponding coordinate system, and the right hand side will be completely independent of the coordinate system. So, the details are left as an exercise. The result is the following, that the curl of a cross product of two vectors is given by B dot del operating on A minus A dot del operating on B plus A times the divergence of B minus B times the divergence of A. So, this result, this identity with A replaced by omega and B replaced by the position vector in the rotating frame of reference can be used to get this result. Okay. So, let us do that. So, all we have to do is to replace A and B respectively by omega and r, which is the position vector in the rotating frame of reference, and when you do this substitution you get the curl of omega cross r. A is replaced by omega, B is replaced by the position vector, and then B dot del becomes r dot del, A is replaced by omega. So, you get r dot del omega minus omega dot del r plus omega times the divergence of r minus r times the divergence of omega. Okay. Now, this term has got the derivatives with respect to space of the angular velocity, right, which being constant, those derivatives will vanish. So, when you have a differential operator which is taking derivatives with respect to space of a constant vector, you will get a 0. So, this term vanishes because you will have the derivative operators which are sitting inside this gradient operator operate on constant vector. So, those derivatives will vanish. Likewise, the differential operators with respect to space coordinates, when they operate on a constant angular velocity, this term will also vanish. So, the first term and the fourth term cancel out, and the remaining two terms, the divergence of this will give you 3. So, this is 3 omega, this will give you minus omega, and the result is 2 omega. So, now you have the result that the curl of the velocity in the inertial frame of reference is given by the curl of the velocity in the rotating frame of reference plus twice the angular velocity, and when this Vr is 0, when the velocity in the rotating frame is 0, the curl of a velocity in the inertial frame of reference is equal to twice omega. So, once again we find that from a linear velocity you get an angular velocity. So, this again suggests to you as to why the operator curl del cross is called as a curl, because it takes a linear property and curls it. Okay. It takes a linear velocity and generates an angular velocity. Okay. We have seen this happen before, which is why the term curl is used. It is like a piece of hair which you can take, stretch it out, but also curl it. Okay. So, that is the reason that this is called as a curl, and it is when you take the curl of the velocity field, it is called as a vorticity, because that is how the vortex currents in liquids are formed. So, now we have got all the machinery of the calculus with us. We have got this essential result which we obtained earlier. You remember how we got this pressure term under the this density term in the denominator under the pressure for the case when the density is not changing from point to point. So, we have already discussed this term earlier in some details. And now let us simplify this, because you have got the half gradient of v dot v, which is nothing but the square of the modulus of the velocity, right. V dot v is just v square minus v of the curl of the velocity, which is vorticity, for which I have used the symbol chi. Chi is the vorticity. So, this is minus v cross the curl of the velocity, which is the vorticity. Then I have got the partial derivative of the velocity with respect to time, and then on the right hand side I have got the negative gradient of these two terms which appear as a sum. Now, I have got a gradient term on the right side. I also have got a gradient term on the left side. So, let me take all the gradient terms to the right. So, I move this term to the right, and when I do so it comes with a minus sign over here, and now I combine all the gradient terms, this one as well as the other one, and write this as a negative gradient of sum of 3 terms, which is p by rho plus phi and this minus half v square by 2 becomes plus v square by 2, because this minus sign I have taken as common outside. Okay. So, on the left side I have got del v by del t minus v cross chi equal to the negative gradient of this term. So, now we can do some special cases. If we take a steady state is one in which the partial derivatives with respect to time vanish, okay. That is the signature of a steady state. So, if you take a steady state, the partial derivative of velocity with respect to time vanishes, which means that minus v cross chi will be equal to the negative gradient of this sum of these three terms which appear in this beautiful bracket. So, you have got minus v cross chi equal to minus gradient of the sum of these three terms in the beautiful bracket. The minus sign is now completely redundant, so you just drop it, it appears on both sides of the equation. So, you can knock it off and you got v cross the vorticity, this is the cross product of the velocity with the vorticity. And now, if you take the dot product of this equation, both sides of the equation with velocity, what do you get? On the right hand side you get v dot the gradient of this term, on the left side you get v dot v cross chi, which is the scalar triple product of three vectors v, v and chi, two of which are the same, therefore, the box product, the scalar triple product goes to 0. So, on the left hand side you have a 0 and on the left hand on the right hand side you have got the scalar product or the inner product of the gradient of these three terms, these three scalar functions with the velocity, which is an identity. Is it always an identity? No, it is so only for the steady state, because we have used that condition. So, if and when the velocity flow is one of steady state, which is when you have nice streamlines formed, okay. So, you have got a steady state, there is no turbulence of any kind, nice streamlines are formed, and what you essentially get is the dot product with velocity of the gradient of these three terms vanishes, and with the velocity field not being 0, and this not being a null function, you can guarantee that the gradient of this beautiful bracket is orthogonal to the velocity, right, because that is when the corresponding scalar product will vanish. Cosine of 90 degrees will vanish, which means that the gradient of the sum of these three functions is orthogonal to the velocity and the streamlines are along the velocity field, which means that the gradient of this function is orthogonal to the streamlines, and we know that the gradient, we know this idea of the gradient was coming from the idea of the directional derivative. Directional derivative is a measure of the rate of change of a function in a given direction, and this gradient is orthogonal, which means that along the streamline there is no change in that function, because whatever change is there is necessarily orthogonal to the velocity field, it is necessarily orthogonal to the streamlines, because the streamlines are along the velocity field when the fluid flow is a steady state flow. Okay. So, for this case the gradient of this quantity in the beautiful bracket, the sum of these three terms I write as a function psi, it is the sum of these three terms which is written as a function of psi. Our conclusion is that the gradient of psi is orthogonal to the streamlines, which means that psi itself is a constant for a given streamline. Okay. The sum of these three terms is a constant for a given streamline. Now, this is a part of the Bernoulli's theorem but I will give you the fuller form. This is after Daniel Bernoulli, as I may remind you. There is a fuller form. This part tells us that the function psi, which is the sum of these three terms, is a constant for a given streamline. This came from the fact that we considered the fluid flow to be a steady state flow when the cross product of vorticity with the velocity was given by this expression. This was the condition that we analyzed. Rest of it was simple algebra. All we did was to take the scalar product with the velocity field. Now we take a further condition, a further consideration, that if the fluid flow is steady state, so that del V by del T is equal to 0, but it is not only a steady state, but also if the velocity flow, velocity field is irrotational. What does it mean? If the velocity field is irrotational, an irrotational vector is one whose curl vanishes. So the vorticity would vanish, and if the vorticity vanishes, then the left hand side vanishes identically. Okay? So when the vorticity is equal to 0, which means that the curl of the velocity is 0, the flow is not only steady state flow, but it is also irrotational, then the left hand side becomes identically 0 because the vorticity is now a null vector. So the right hand side becomes a null vector. So the gradient of this function becomes 0, which means that the function itself is a constant for the entire velocity field, not just for a given streamline. Okay? If it is a constant for a given streamline if the fluid flow is only steady state, but it may have vorticity. But if it is also free of vorticity, if the vorticity chi is 0, if the velocity field is irrotational, then you have got the entire function psi to be constant for the entire field of the velocity, not just for a given streamline. So this is Daniel Bernoulli's theorem, and we have obtained it using vector calculus, and this connects to the work energy theorem in which the Bernoulli's principle is very often interpreted in high school books. Okay? In ordinary school books, this is often interpreted in terms of the work energy theorem, because what you do is, if you consider a rectangular parallelepiped in a medium through which fluid is passing, and then you apply the divergence theorem, that the divergence of a vector, if you take the volume integral of the divergence of a vector, then it is equal to the surface integral of the vector taken over a closed path, closed surface, which encloses the corresponding region. And this is really the equation of continuity that we have discussed in unit 8. Okay, we have discussed this already in unit 8, and we will use that result coming from the equation of continuity for the steady state and find the work done on the fluid by the pressure that the fluid exerts on phase 1. So there are these two phases, EFGH is phase 1 and ABCD, this is the phase 2. So the work done on the fluid by the pressure of the fluid which exerts this pressure on the phase 1 will be force times displacement, that is the work done, right. Work done is given by force times displacement. Force itself is pressure times area of the phase 1 times the displacement, and the displacement itself is velocity multiplied by the time taken to cross that segment. So the segment we are talking about is this linear segment from phase 1 to phase 2, this is the segment. Okay. So V1, so it takes, let us say, delta t, a small time interval delta t, to cross this segment. So, this work done on the fluid by the pressure that the fluid exerts on phase 1 is P1 A1 V1 delta T, whereas the work done by the fluid on the phase 2 is given by an exactly similar consideration, which is F2 delta S, which will be P2 A2 V2 delta T, right. It is exactly the same consideration, and that tells us what is the net work done on the fluid in the parallelepiped. Work done by what? By the pressure of the fluid, which the fluid exerts on phase 1 as well as 2. Okay. So, that must be obtained by the difference of these two works done. So, you subtract the work done, this delta W2 from delta W1, and this difference is given by the difference between these two quantities. So, P1 A1 V1 delta T minus P2 A2 V2 delta T is this difference. So, let us interpret this particular difference. We will now consider that a certain amount of work done on the fluid is what we have determined. Where is this work going to go? It will go as the energy gained per unit mass by the fluid as it traverses that, right. Energy can neither be destroyed or created. So, now that some amount of work has been done on the fluid, it has to manifest through conservation of energy as something. So, it will manifest as the energy gained per unit mass by the fluid as it traverses that particular distance. So, that energy difference is that energy gained is E2 minus E1, right, and that will be this difference divided by delta m, which is the energy per unit mass. So, all I have done is to write this expression now in terms of the E2 minus E1. What is the net energy over here? This is the kinetic energy per unit mass. Half mv square is the kinetic energy, but we are determining the quantities per unit mass, which is why the m does not appear. Okay. So, this is the kinetic energy, this is the potential energy, plus there is some internal energy which the liquid has. So, this is the total energy E on the phase 2 minus the corresponding energy on the phase 1. So, this is the difference E2 minus E1, and this is what appears as the energy gained per unit mass by the fluid as it traverses the x axis when the liquid passes from left to right from phase 1 to phase 2. So, here we go, we have just written that relationship. So, this left hand side P1 A1 V1 minus P2 A2 V2, this whole thing multiplied by delta T divided by this mass element, and this is volume into density. So, the density is rho, the volume is the length segment times the area. So, delta S times area is the volume, and on the right hand side you have got the difference of these two energies. So, let us write this result at the top of the next slide, which is here. And now you can cancel the common terms very easily. So, I have only separated these two terms now. So, I have got P1 A1 V1 times delta T divided by this rho V1 delta T. Delta S is nothing but the velocity times the time interval, right. This is the length delta S, that is the distance which is traversed, and that distance is velocity times the time interval. So, this is the velocity V1 times the time interval, and from the second term you have got from this second term over here, again this is the velocity times the time interval, and now you can cancel some of the common terms because there is an area A1 here, there is an A1 area over here. So, these two terms cancel, then these two V1s cancel, right. Likewise, these two A2 elements cancel, the corresponding velocities cancel, and now this delta T cancels the delta t in the denominator over here, and there is a delta t in the denominator here as well. Okay. So, the delta t also cancels, and that simplifies the expression quite a bit. So, you have got P1 over rho minus P2 over rho equal to half V square plus phi plus U internal for the phase 2 minus half V square plus phi plus U internal for the phase 1. And what are these subscripts 1 and 2? They correspond to the two phases, the phase 1 and the phase 2, right. And whatever value you have, if you combine all the terms for the phase 2, and here you have got the corresponding terms for the phase 1. So, you move these terms P1 by rho and P2 by rho also to the right side, but when you do that you must change their signs. So, P1 will go with a minus sign. So, P at the phase 1, which is P1, goes with a minus sign, but P2 when it moves to the right has got a minus sign over here. So, when it moves to the right it goes with a plus sign. So, you have got the pressure term over here on the phase 2 and it has come with a plus sign. And what you find is that these two brackets must be equal, they have got opposite signs, and therefore they must be equal, and therefore they do not depend on the subscript 1 and 2, no matter what the indices are, whether you take it on phase 1 or phase 2 or phase 3 or phase 4. Okay. No matter what you do, the quantity inside this bracket must therefore be constant, because they are independent of the location on the x axis. It is the location on the x axis which is indexed by the subscript 1 and 2, which is exactly the Bernoulli's principle which we got from vector calculus. We showed that the pressure over density plus phi plus V square by 2, which is what we have got over here, the P by rho is here, the phi is here, and the kinetic energy is here. This is the kinetic energy per unit mass. The only thing which is in addition over here is the internal energy. So, this is basically a conservation of energy statement, which is how it is interpreted in high school books, and we have found that this is the constant for the entire velocity field in a liquid when the velocity flow is a steady state flow and also when it is irrotational. But if it is only steady state flow, but if the vorticity is not 0, then we know that this is the constant only along a given streamline. So, this is an extremely important theorem in fluid dynamics, and this has got applications in various kinds of things, and I think what youngsters like to see is its applications in sports. And a question which you might want to ask is, if there is a cricket match, and you can have all kinds of cricket matches these days, you can have a 5-day cricket match, a test match, or you can have it over a single day, a 50 overs match, a 50-50, right, a 1-day test as you call it, or you can have a smaller version, the 20-20. Okay. And what kind of a cricket ball would you use? Would you use a red ball, or would you use a white ball, or would you use one which is half red and half white, or half yellow and half red? Okay, there are all kinds of cricket balls which are manufactured, and you might have noticed that people use different kind of cricket balls for different kind of matches. And the reason, of course, is the fact that in a shorter version of the match, it is the swing bowlers who play a big role. I am sure you would have noticed this, that each team tries to pack its bowling squad with in swing and out swing bowlers, because what they do is they rub the ball only on one side, and then what it does is that the ball is more rough on one side than on the other, so that the rougher side carries the velocity with a drag. Okay. So, there is a velocity difference on the two sides of the ball, and if there is a velocity difference on the two sides of the ball, then the sum of these three quantities being constant, if the velocity term is different, then the pressure will have to be different. So, if the velocity is more on one side, then the pressure on that side will be less. If the velocity is more on one side, then the pressure on that side will be less. So, there will be a pressure gradient across the ball, and it is this pressure gradient which will swing the ball when it is moving through the fluid. Okay. So, this is what the swing bowlers exploit, and they prefer to use the white ball because it has got a thin lacquer that is applied to its surface to avoid discoloring, and then during the play what they can do is the shiny surface remains shinier and the other one starts becoming rough. So, what they are trying to do is to exaggerate this difference between the smooth surface and the shiny surface or the smooth surface, because the more they exaggerate this difference, the more velocity difference they can generate, and the more velocity difference they generate, the more pressure gradient they can generate, and the more the ball would swing. Now, you know how to swing the ball, it does not mean that you will be able to swing it. So, if Ishant loses his place in the cricket team, does not guarantee you a chance. But anyhow, this is fun. And there are some people, this Ravindra Mehta for example, who was a graduate student somewhere in the late 80s, and he studied all these dynamics of sports balls in all kinds of situations, the cricket ball, the football, the soccer ball and the tennis ball, and he did a lot of this survey. So, a lot of this is available at his website, and there are some very interesting papers on the swing of a cricket ball in flight, and this is published in major journals, like this is published in the Proceedings of the Royal Society of London. Okay. Then the effect of humidity on the swing of cricket balls in International Journal of Mechanical Sciences, and maybe one of you wants to do a PhD on this because there is enough to work on. This is connected with the Magnus effect, and this Ravindra Mehta, if you go to his website you will find many more references. So, I will let you go to that and enjoy it. So, as I mentioned, there are a number of very interesting papers on the dynamics of sports balls and cricket players, swing bowlers, tennis players, soccer players. They all exploit this when they are playing their respective games, and they can make the ball which they hit and make it swing in a particular direction depending on how they control the movement of the ball. And the Magnus effect is a very fascinating effect. It involves the drag, and the actual dynamics is quite complicated, but the Bernoulli's principle in its very basic form does play a very important role in the dynamics of the ball's swing. Now, let me invite Otonu to show you a very simple experiment. So, Otonu, will you just come up with those sheets of paper which you have with you and just come up to this place, and what Otonu is going to do for us is he's holding two sheets of paper and he's going to blow air in between. So, what do we expect? We think that the papers are going to fly off from each other. So, Otonu, would you just blow air in between? Yes? Yes? So, what do we see? Yeah, there you go. Just do it one more time. Very good. Yeah, what do you see? Thank you, Otonu. So, what we see is that the paper sheets really do not fly away from each other, but instead they get dragged toward each other, they get closer, and it is once again because of the conservation of energy that we have seen in the Bernoulli's expression. What is happening, Otonu, is that when the speed, the velocity of the air in between the two sheets is reducing, then the velocity of the air in between the sheets goes up, because that is where you are blowing the air, and if the velocity goes up the pressure drops, and then the pressure outside the sheets is larger. So, that generates a pressure gradient which pushes the sheets toward each other, and this is the reason that the sheets, the paper sheets actually get sucked in toward each other. Now, this was a relatively straightforward experiment. It did not cause any damage to the pieces of paper when they came closer to each other and hit each other. The paper sheets remain intact, but let me show you some damage which is there on this slide. That these are two ships. One is the ship on the left is the ship by name Olympic, and the one on right is Hawk. And what had happened is that the displacement of water when these two ships were in the sea, this was I believe in 1911 September 20th, if I remember right. And what happened on this fateful day is that the water which was displaced by these ships, which were not too far from each other, but the displacement of water generated velocity currents in such a way that the velocity of the waters in between the two ships increased, just the way the velocity of air between the two sheets of paper in which Otonu was blowing increased, and then the pressure outside pushed the two ships toward each other, and look at the damage that is caused. This is the ship Hawk. This is enormously damaged. There is a hole over here, and if you are able to read this note, the damage below the water line was actually much greater than the damage above, and these ships belong to the family of ships like the Titanic, and the accidents actually took place around the same time. So, in fact, this is the Olympic Hawk collision. Yes, indeed it is 20th September 1911, and this is what caused the damage of the Olympic, which was sucked into the Hawk on the side, and that caused a good bit of damage. There was one crew member of the Olympic by name Violet Jessup who survived the collision with the Hawk, and he also survived the collision in which the Titanic sank, which some of you would have seen in that very famous movie. And subsequently there was another ship which sank, which was Britannic, and our man Violet Jessup survived that as well. So the Bernoulli's principle appears in some very fascinating stories in voyages through the sea. So here is the damage that you can see, and in the next unit we will apply vector calculus to electrodynamics, to classical electrodynamics, which is an essential part of classical mechanics. Okay. So, classical mechanics distinguishes itself from quantum mechanics, but in the entire domain of classical mechanics, when you apply it to electromagnetic phenomena as well, you must invoke the special theory of relativity, because the special theory of relativity is intimately connected with classical electrodynamics. So, this will be the subject of our discussion in the next unit, but at this point I guess we could take a little break. So, the next unit will deal with electrodynamics and the special theory of relativity. The electrodynamics of course comes from James Clerk Maxwell, and the special theory of relativity from Albert Einstein. So, at this point I will ask a few questions. I will ask for a few questions so that you can ask some questions, and then we will of course study the Maxwell's equations. You notice that you have got the divergence and the curl, and as I mentioned, through the Helmholtz theorem you do need both of them to specify a vector field. So, to specify the electromagnetic field you need both the divergence of the vector field E and the curl of the vector field E, and also the same for the magnetic fields. So, any questions, comments?